Welcome to the Potter's Roundtable, a monthly podcast where we share our passion for the ceramic arts and a collection of topics specific to potters. Remember to subscribe so you don't miss a single episode. Enjoy the show.
Okay, well, today's topic is a discussion of gas-fired kilns, and this is a continuation. This is part of the three-part series we've been doing on Introduction to Pottery Kilns. And I called it Introduction because I didn't want to scare people off. I didn't want to get too technical, and I wanted to attract people that had a range of backgrounds so that if somebody didn't know anything about it, they'd feel comfortable coming, but also have enough depth that if somebody had some experience, they could also come and maybe learn something. So I've been doing it, this is a three-part series, and I'm doing them sort of in historical order. The first part, the last one we did last month was wood fire. This is going to be gas, and then next month will be electric. And then the month after that, I'm going to do a talk on problems that occur with firing in general, problems that occur actually in the course for operating the kiln, and whether or not those problems actually affect the work or not. So it'll be sort of an overview of firing problems that occur with the kiln or problems that result in the wear. So, but just to review basically, what is a kiln? And you can define a kiln as an enclosed space or an enclosure for controlled heating. So you can, if you ask the question, why do we need a kiln? One of the main purposes, or the reasons why you actually need a kiln, is for reproducible results. You can't get the whole purpose of a kiln is to be able to control your firings, and without some kind of an enclosure and without some kind of controls, you can't reproduce your results. And the other thing is, you can't get to high temperatures without a kiln. You can only reach very low sort of bisque level temperatures with open pit firing. So unless you can control the heat loss, you can't reach high temperatures. So you really have the two reasons for a kiln. You have kilns for control, and you also have them to enable you to get to higher temperatures. A little background also, basically we're talking about gas-fired kilns on combustion. Basically, you're going to be burning some kind of a gas. It'll combine with oxygen. And the three things that you make, if you do that, you make carbon dioxide, you make water vapor, and you make heat. And so we've got the two exhaust gases that we're reducing, carbon dioxide and water. There are two types of gas that are commonly in use now for pottery kilns, natural gas and propane. Natural gas, essentially, what we're really burning is methane. That's the gas that's in it. And natural gas is just a naturally occurring gas. It's typically found with petroleum or sometimes in deposits by itself in the ground. And it's supplied as a public utility through pipes to the point of use. So that in metropolitan areas or usually larger towns, it's basically plumbed into your house or plumbed into the use. And where it's used in residences, it's used at very low pressures. This is an important thing we'll talk about more. Because for safety reasons, they don't want to be supplying gas at high pressures to a house, because if you had a leak, too much gas could escape before the leak was even detected, and you could have potential explosion or fire problems. So it's supplied typically at around 1/4 of a PSI. That's 1/4 of a pound per square inch. Gas pressures are measured in pounds per square inch. And typical natural gas to the house is 1/4 of a PSI. There's another unit that's used that you'll see it if you look into natural gas supplies, and it's called inches of water column. Inches of water column, I'll just abbreviate it. And what that means is, if you were to take a tube, this is where the term comes from, and you put water in it, like a U-tube like that, and then if you to connect a hose to this end and push gas in it, the pressure of the gas would raise the level of the water up. And so that's inches, that's the water column of the water in that little tube. So 1/4 of a PSI will raise this water in this tube up about 7 inches. So this is called 7 inches of water column, because it's a more sensitive way of measuring very low pressures compared to PSI. But it's equal to about 1/4 of a PSI. But it's very low pressure compared to other, I mean, like if you think about it, like your car tires have 35 PSI in them, or they might have 40 PSI in the air in your tires. This is 1/4 of a PSI, so it's very low. The second gas that's commonly used most commonly used for gas kilns is propane. And this is actually a byproduct of natural gas production. Natural gas is piped across the country in pipelines, and in order to do it efficiently, they actually put it under pressure so they can compress the gas and fit more gas in the pipeline. Well, one of the problems, if propane occurs naturally in natural gas, and they have to separate it out, because propane, when you put it under pressure, easily liquefies. It turns into a liquid. Well, they can't have liquids forming in the pipelines. So they separate the propane out from the natural gas, and it's a byproduct that they sell separately. But propane is supplied as a liquid in tanks. It's not piped in anywhere, and it's usually delivered in tank trucks, and then it's transferred to your own tank that you have on your property. But it's transferred as a liquid under pressure, and it's also typically used at a lot higher pressures than natural gas because it's just coming from a local tank. It's not in underground pipelines. It's typically used at 10 or 20 or 30 psi, used at higher pressures because it's not. You can't get propane piped into your house. Unless it's for something special, like maybe you might have a gas stove that runs off of propane and there'd be a special line that would come into your house. But it's not a public utility. It would come from a tank, a special tank in your backyard or on your property. There are several differences I wanted to talk about between natural gas and propane, just talking about the fuels. I mentioned that propane is supplied as a liquid under pressure. And the idea is I have a tank that's full of liquid propane. This is true of all propane, including your little barbecue tank. It's a liquid. But it's under pressure in the tank. And when you open the valve, the liquid propane actually boils and gives off propane gas vapor. And that's how it's used. And the reason why this works is because liquid propane boils at 44 degrees below zero, which means that anything within the normal temperature range that we live, unless it's under pressure, it's going to be a gas. But they can pressurize it and turn it into a liquid. And then the minute you open the valve, it's way above 44 degrees below zero. So it'll immediately boil and produce propane gas, propane vapor. Fahrenheit, yeah, minus 44 degrees. So this we'll talk about this later on, but then this affects how you use propane, because if you have a propane tank outside and it's really cold outside, like I lived in Maine and it was 20 below zero, when you open the tank, you don't get much pressure because it's not that high above the boiling point, and so it doesn't boil that vigorously, so you don't produce that much gas. So the pressure that you get from a propane tank can depend on the outside temperature as to whether it's boiling really vigorously or not. There's another factor here that propane, it's said that propane gas burns a lot hotter than natural gas. That's not true. That's a myth. It burns slightly hotter than natural gas, but the reason why people got that impression is, or they came to that conclusion, is that the same quantity of propane gas yields a lot more heat than the same quantity of methane. And the reason, and you go back to the chemistry of that, it's easy to explain. This basically, in a certain volume of natural gas, there's a lot less fuel. Methane, this is the formula for methane, CH4. So there's one carbon and 4 hydrogens. The formula for propane is C3H8. There's just, both of these things are burning. This is making carbon dioxide, this is making water. So there's just a lot more fuel in every molecule of propane than there is in every molecule of methane. So if I have a certain quantity, let's say a cubic foot of methane gas or a cubic foot of propane, there's just a lot more potential energy that I can get out of the propane than I can out of the methane. So it doesn't burn a lot, it burns slightly hotter, but not that much hot. But it's significant because you get a lot more energy out of it, out of the same quantity. Which means that, for instance, to produce the same amount of heat, you have to burn a much bigger volume of natural gas than you do for propane. So this is where I think this myth came from, that it burns a lot hotter, because they say, oh, it's real, propane is really effective. Well, it's because you're getting more energy out of it, getting more heat from the propane. Another important difference is that propane gas is heavier than air, and natural gas is lighter than air. And this is a safety issue, because if you have a leak in a propane device, the propane will sink to the bottom of wherever it is, and it can collect in a pool. So that if you have a kiln that's pretty tight and you're blowing propane into it and it's not burning, it'll literally collect in the bottom like a pool of water. and it won't dissipate that quickly. And then if you put a match or something in there, or you try to light it again, you've got an explosion. You get this big reservoir of fuel. Natural gas is lighter than air, so that if you get a leak, it tends to rise and disperse. But propane doesn't. This is also why it's a hazard in houses. This is why they don't normally put it in as a normal rule, because if you had a basement and you had a propane leak, you'd fill up your basement like a swimming pool full of propane gas. And it would either explode or you'd walk down into it and suffocate. When I worked in industry, we had different kind of tanks, and there was a situation where a couple of workers died because they drowned in gas. They drowned in propane gas. There was a large tank, and there was a propane leak, and they went in to do maintenance work on the tank, and they didn't know about it, and they didn't have the safety things in place, and they climbed into the tank, and they climbed down a ladder inside the tank. Well, propane gas had accumulated in the tank, and they got below the water, and they drowned just as if they were in water. And they found them at the bottom of the tank. And when they found them, there was still propane in the tank. It just had leaked and filled up this tank. And there was an event. And they just climbed down the ladder and passed out and drowned in the propane, just as if it had been in water. Another difference is, since natural gas is used at low pressure, you need larger pipes in order to supply it, because you don't have a lot of pressure pushing the gas through to get the quantity, the volume. So you need much bigger pipes supplying the propane, the natural gas, to your kiln or whatever you're using it for, than you do for propane. With propane, you're operating at higher pressures, so you can have smaller pipes and still get the same amount of gas. Plus, and as a segue, a good segue, is that if you're connecting to natural gas, since it's a utility, you need a permit and an inspection of your kiln. So you have to have your whole setup inspected, because they're not going to let you hook up to the natural gas unless they're sure that the whole setup is safe. And this is a problem because they're not used to inspecting kilns. They know how to inspect a stove, or they know how to inspect a barbecue, but they don't know how to inspect a kiln, especially if it's a kiln that you built yourself, not a commercial model. And so that can create problems with getting permits and getting inspections and just getting permission to do it. With propane, I've had propane in a lot of different locations. There's generally no permit required. Some cities will require it, but generally not. And so what you do is you work with the propane company to get a safe installation. And you just work with them. And they have guidelines and regulations, like depending on the size of the tank, you're only allowed to put that within a certain distance of an ignition source or spark. And so they have guidelines that they follow. And so generally with propane, you work with the propane supplier in terms of ensuring that your setup is safe, but there isn't any sort of government involvement. There are three primary design sort of features of a gas burning kiln, and they're basically the same as for a wood burning kiln. You've got a heat source, you've got a wear chamber, and you've got a chimney. In this case, though, the heat source, now we're talking about gas rather than wood, the heat source consists of gas burners, and an important part of that heat source is air inlets. You need a place in the kiln for air to get into the kiln. And then you also need a separate combustion chamber or a combustion space. And we'll talk a little bit more about that. But the gas, when you let the gas and the air into the kiln, they don't immediately mix. And in order to get efficient burning and also not mess up your pots, you want to get the gas and the air as well mixed as possible before you light the flame. Because otherwise, if you think about it, if they're not mixed, you've got gas hitting your pots and you've got air hitting your pots, so you can get oxidation and you're not getting efficient burning. So you really want to provide a mechanism or a space for the gas and the air to mix thoroughly and then burn and then get into the wear chamber. So this is an important aspect, and it was true also in wood burning. You need a space as much as possible for the burning to happen before the flames hit the pots, before the flame hits the work. But one of the advantages of burning with gas is that just because it is a gas, you can get, right at the start, there's the possibility of getting a better mixing of the fuel, the gas, and the air, better than you get with wood. One of the problems with wood is you've got a solid fuel, and so how do you mix air with a solid chunk of wood? Well, you're burning the gas. I mean, you're burning the gases coming off the wood, but you still can't get as efficient mixing. So you have the possibility of getting much better, much more efficient mixing and more efficient burning with gas than you do with wood. And there are two, so now as far as gas burner designs, there are two main designs or two main types of burners. They're called Venturi, which is also called atmospheric burner, Venturi burner. Venturi, and it's also called an atmospheric burner. And the second kind is a forced air burner or a blower burner. And let me draw a little sketch up here on the board. A Venturi burner, the nice feature about that is, by itself, it can draw in air that it needs to burn. So if a Venturi burner sort of looks like this, and I've got one here on the table, I'll show you in a minute, but these are the basics of a Venturi burner. So I have gas coming in here, and this long tube, that's this tube right here. And this constriction right here, what happens is when the gas this is gas under pressure. So when the gas comes into the burner under pressure, when it hits this constriction, the gas actually speeds up. It has to speed up to get through this constriction. Well, when it speeds up, it locally actually creates a little bit of suction around the area where it's speeding up. And so it creates suction back in here where it's speeding up. And so what that does is that tends to draw in air here. So I've got gas going through the burner, and I'm drawing in air, and so the gas and the air have a chance to mix, and the flame is out here. So I have gas and air mixing in the burner before they even reach the flame. So they have a chance to do some mixing before it even starts burning. And the nice thing about this is I don't need any power. I don't need any fans like you do with the other kind of burner to get the air into the kiln. The burner itself tends to draw in the air. And this line that I've drawn here is a plate on the back. This is a Venturi burner, this big thing. And I didn't show it here, but on the back there's a disc of metal that you can turn and open and close the gas. And this is where the air would go into the burner back here. This is the narrow part where the gas speeds up. And so it creates suction right here. And air is drawn in right here and has all this distance to travel to mix with the gas before it comes out the end and burns. This is a diffuser tip or a mix. The burner actually ends here, the Venturi part. This is an additional tip that's put on that helps to further mix the gas and the air and make sure that they're well mixed. So the nice thing about a Venturi burner is it's bringing in, at least not all, but it's bringing in part of the air that it's need to burn, and right in the burner, the gas and the air are mixing. Before it even gets into the kiln, I'm getting some, because this normally, you wouldn't have the burner sticking into the kiln, you'd have it on the outside. So you have some gas and air mixing before it even gets into the kiln, which is an advantage. But the forced air burner doesn't draw in, basically it uses a fan, and it uses a blower to blow air in, and really simply, a forced air burner might look like this. And this is a fan, looks kind of like a hair dryer, but that's the idea. This is a fan blowing air, and this is a gas line, and the gas comes down and is injected into the airstream, and then there's my flame. So, but in this case, I need an electric motor or some kind of a motor to run the fan to blow the air in. And again, but in this case, I can get very efficient mixing, and I can put in as much air as I want or as much gas as I want independently, so I can get very good mixing with this kind of a burner. With this kind of a burner, I don't need a chimney because I don't need to draw in any extra air. This can supply all the air that I need to burn all the fuel that I need, and I can just vary the air, and I can vary the gas and the air independently. So I have full control. With a Venturi burner, I have limited amount of control of the air, but with most Venturi burners, I'm still not getting all the air I need to complete combustion. So I need additional air. I need what's called secondary air, and for that I need a chimney. So a lot of cases, these are used, for instance, on kilns that are indoors, in an indoor facility, because I might need an exhaust pipe, but I don't need a chimney to create a draft, because I don't need to pull in any air. I just need to get the gases out of the kiln.
If you have a chimney, then you would need other air flow.
Then I need air inlet into the kiln for the secondary air. We'll talk more about this, but at least for this kind of for a blower burner. But the problem here is I need power for this. Whereas I've had propane kilns off in the middle of the woods, and you have a propane tank, and that's all you need. That's all you need to operate it. Whereas this, I need electric power to run the fan, or some kind of a power. Okay, so those are the two main kind of burners, And as I say, the example I have up here, this is a Venturi burner, and that this Venturi, this is an old principle that was, it's also called the Bernoulli Principle. It was a scientist who discovered that when you study gases, that if you cause a gas to speed up, that when or to go through a constriction, it speeds up, and when it does, it actually creates local pressure. This is the same principle when cars had carburetors. This is the same principle that made your carburetor work in a car. You had same idea, exact same idea. When you only in a carburetor, you had a throat like this, and when you drew in air through here, this is sitting on the top of the engine, you had a little nozzle coming in like this that drew in the fuel. So this created suction and pulled the fuel in. It was the same idea. You suck in air and you bring it through this constriction, creates a local air vacuum, and draws in the fuel. Okay, burner sizes. How do you know, how are burners sized? Burners are rated by the amount of heat output, and they're rated in a unit called the British Thermal Unit, which is a BTU. So burners are rated according to how many BTUs per hour they produce. This is a BTU. This is an abbreviation, BTU. It stands for British Thermal Unit. It's an amount of heat. And just as an example, one BTU is not a lot. 1 BTU is the amount of heat it takes to heat a pound of water 1 degree Fahrenheit. That's a BTU. Or it's the amount of heat you get, the total heat you get when you strike a wooden kitchen match. That's about 1 BTU. So a typical range of and since you're firing, you want to know it's also time. So it's BTUs per hour. Even though the shorthand, people say, well, that's so many BTU burner. What they mean is BTUs per hour. So typical burners might be anywhere from 50,000 BTUs. This is a 500,000 BTU burner. So 500,000 BTUs per hour, this burner will put out. And they go on up from there. But typical pottery burners are roughly in that range, 50,000 to 500,000 BTUs per hour. And the burner size is based on the kiln design and the kiln size. Because basically what you're saying is, how much heat input do I need to raise the temperature of everything in the kiln and do it fast enough so that I offset the losses? Because when you're heating up a kiln, you're losing heat constantly. Heat is just coming off from the kiln. And actually, when you talk about that, most gas kilns are, when you talk about efficiency of a kiln, what you're really talking about is how much of the fuel that I put in is actually going to heat up what I want to heat up, meaning the pots. Now we've got kiln shelves in there, we've got coats, and we've got the kiln itself. That's all basically wasted heat. Because all I really care about is heating up the stuff, the pots. Well, most gas kilns are roughly 5% efficient. Roughly 5%, might be 8%, maybe 10, not commonly. But as a round number, 5% is a good efficiency number, which means that 95% of the fuel you're burning is wasted. And that's normal. This is normal, okay? And the problem is, which we'll talk about again later, is as you heat, this is just a law of physics, as you heat things up, the higher you heat them, the faster they want to lose heat. So it's like running up a hill and you're trying to get to the top of the mountain, but as you're running up the hill is getting steeper and steeper and steeper, and so you have to run faster and faster and faster. So that in order to fire a kiln and in order to determine the size burner you need, you have to say, how much stuff am I heating? That means the bricks in the kiln, that means the pots, the shelves, everything. How much heat do I need to heat that up fast enough so that it doesn't lose heat so that I can actually raise the temperature? Because at some point, I might be putting in heat fast, just at the same speed that it's being lost, and I'm never going to get it any hotter. The heat is being lost from the kiln up the chimney, out through the walls, and I just simply can't get it. So I've got to be able to overpower it, basically. I have to be able to get more heat in there faster than it's being lost to keep the temperature rising. And that's the thought process you go through if you're saying, what size burner do I put on my kiln? And this is a problem that people run into with some of their kilns. If the burners are undersized, then they go to heat it up and they simply can't get it to the final temperature because the burners simply cannot put out enough BTUs per hour fast enough to overcome the heat that's being lost. Okay, I want to talk a little bit about burner hardware. And I think what I'll do is I'll do a little sketch here on the board of the typical setup for the two kinds of burners. There are two things to think about when you're using gas, and they're not the same. And this is important in terms of running a gas kiln. One of them is pressure, and the other is flow. And so the pressure is the amount of push that the gas is exerting. I can adjust the pressure of the gas that's coming to the kiln. And I can also open a valve and if I fix the pressure, I can open a valve and let more gas come out at that pressure. And I have both of those controls. I have a valve here, and I have a pressure regulator. So I can do both of those things. And those are the two things I have to work with. What's the pressure? What's the push? And how big is the hole in the pipe, essentially? Or how big is the pipe that I'm letting the gas come through at that pressure? So if I'm at a certain pressure and I open the hole more, I get more gas. Or if I keep the hole size the same and I turn up the pressure, I get more gas. So I can do both of those. Right, either way. Okay, so just in terms of a setup, I'm just going to draw the basic components really quickly, the basic components of a gas thing. And this is going to be very diagrammatic. So this is a gas tank. This is for propane. I have a gas tank. And on the gas tank, I'm going to just abbreviate it here. This is going to be a primary regulator. Plus I have a shutoff. I'll talk through it in a minute. I just want to get it up here. Primary regulator shutoff. And then I go to another shutoff valve. I'm going to draw it, and I'll just draw it, and I'll talk through it in a minute here. Okay, these are basic components for a gas setup. So I've got, and I'll talk through. So this is my main gas tank, and this is where I've got my liquid propane in here. Okay, liquid propane. So I've got the first thing I've got, and this is on the gas tank itself. I've got a shutoff valve, and I've got what's called a primary regulator, and that determines when I open the valve on the tank, what's the pressure coming out of the tank, because there's a lot of pressure in the tank. It could be well over 100 psi in the tank, much more than I need. Okay, so I've got a shutoff valve. I open the valve, and I've got a regulator, and then this is called my line. So this is the tank. Normally the tank would not be, all this stuff is at the kiln. So there's some distance between the tank and the kiln for safety reasons. So one of the things I do is I establish what's called line pressure. Like how much pressure do I want in the pipe going to the kiln? And the tank might be some distance from the kiln, in which case I have to offset the fact that I'm going to lose pressure just going through the pipe. So this pressure regulator here establishes what's called line pressure. How much pressure do I have in the line that's going to go to the kiln? Okay. And then I have a shutoff. So this is now I'm at the kiln. This is a shutoff valve. This is my safety valve that if I have to, I can shut off the gas to everything at the kiln. That's the first thing I usually have in the line. I can kill the whole kiln. Okay. Then this is a secondary regulator. This is a regulator which looks just like this. That's what this is right here. And attached to the top of it is a pressure gauge. And so now what I want to do is I want to reduce the pressure from the line pressure to whatever the best pressure is to operate on the burners. And I don't normally need, really, for a lot of burners, I don't need 50 psi or 30 psi, 10 or something like 15. So I use the secondary regulator now to adjust it down to whatever the best pressure is for the burners that I'm using, okay? So now I've got pressure coming out of here, which is a lower pressure, and it's what I'm gonna fire the kiln with. This is my Basso valve. This is my Basso. That's this thing right here. And this is a safety device. And then as part of the rest of the set, the Basso valve has everybody know what a thermocouple is? Temperature sensor? It has a thermocouple that comes out the bottom and sticks into the flame. And the whole idea of the Basso is if the flame goes out and the thermocouple doesn't get hot, the valve shuts off all the gas. That's the purpose of the Basso. So I've got two lines coming out of I'm sorry, wait a minute, I drew this wrong here. I've got two lines coming out of the out of the Basso. I've got the main gas line coming through it. That's one of these big pipes. But also off the side, I've got a line to this is a pilot burner. I've got a gas line going to the pilot. And the way it works is this. There's a button on top of when I'm lighting the kiln, there's a button on top of the Basso, this one right here, that I can push down. And I push that down and I hold it. And when I push that down, that allows gas only to the pilot burner, to this extra burner here. And while I'm holding it, the gas goes to the pilot and I can light the pilot burner. And then the thermocouple detects the heat. And if it's hot, it says, okay, my pilot light is going. Now I can let the gas through the main pipe. So it automatically lets the gas through to come to the main burner then. Okay, and once the pilot is lit and the thermocouple is measuring it, I can let go of this button. I don't have to hold the button down anymore, and I can let go slowly, and the pilot stays lit because the thermocouple is telling it, okay, it's hot, I can keep the valve open. And then it opens the main valve, then I can open this valve here and turn on the main burner. And the pilot will light the main burner. And the whole point of this is the fact that if this burner were to go out during a firing, which can happen in a windstorm, sometimes if the burner isn't adjusted properly, I'm pumping gas into the kiln, I've got a potential bomb. So the whole idea is if the burner were to go out, the pilot would immediately relight it. And if the pilot isn't going so that it can relight it, the Basso shuts it off. So that's the idea. That's the safety device. So this is the normal sequence that you would want all these things. You'd want a main shutoff valve. This is the one that kills everything immediately. So if I had a problem with, I was worried about it or something, I can. This is right at the kiln. I can shut it off. I want a secondary regulator to reduce the pressure to a working pressure. The Basso valve. This is the valve that I use to actually fire the kiln with. Because now I've got gas coming out to the main burner. This is the one that I open and close. It's a ball valve. And it's basically inside the valve body, you can look at it later, there's a ball that has a hole in it. And as I turn the valve, the hole lines up more or less with the hole through the pipe. And so I end up with this sort of crescent, looks like the phases of the moon. I end up with like either a crescent-shaped opening or a full opening. And that's the one that I actually use to control how much gas is getting to the kiln. So when I fire it, I set the secondary regulator to some pressure. And then I open this valve, increasing amounts to get the temperature to rise. Okay, so that's what all the components are here. This is the shuttle. I don't have the valve here that controls the kiln, but this is the gas would be coming this way. This is my main shutoff valve. This is my secondary regulator and pressure gauge. Now I've got my Basso valve, and on this piece right here, this is the thermocouple lead. This one would plug into the bottom of the Basso like that. That would plug in like that. This is my pilot burner, and there's the thermocouple tip. So this senses whether the pilot burner is lit, and it plugs back into the bottom of the Basso valve, and then this pilot burner keeps this lit.
We hope you're enjoying the show. Please take a moment to leave a 5-star review on your podcast platform of choice. It really helps new listeners find the show. Don't forget to subscribe to receive updates as new episodes are released. And if you'd like to support the video and podcast production of the Potter's Roundtable, become a patron. Go to patreon.com and search for the Potter's Roundtable. Your support will help us achieve our goal of creating a digital library spanning the ceramic arts for use by educators and artists alike. Thank you for your support. Now let's get back to the show.